the cold silence between stars, where light itself travels for centuries without finding a listener, something began to move. It did not shimmer like a comet or blaze like a star reborn. It drifted slow, deliberate, almost remembering a direction it once knew. Against the black canvas of interstellar night, this faint traveler caught the soft glint of a distant sun, its surface scattering light in strange, uneven pulses, as though breathing in the emptiness. Astronomers would later name it 3-Eye Atlas, but in those first moments of discovery, it had no name, only the quiet astonishment of being seen. Every mystery begins with curiosity. Subscribe and keep the search alive. The telescopes that caught it were meant to find comets, those icy relics bound to our sun's command. Yet this one defied gravity's reach, cutting across the solar system at impossible speed, on a path that led from nowhere and to nowhere. It was only the third interstellar object ever detected, after Oumuamua and Borisov, but even among anomalies, it was the strangest. Its light curve flickered without rhythm, its trajectory bent where no force should act. Its spin should have shattered it into fragments, yet it remained whole. The laws that shaped every planet and asteroid seemed to unravel in its wake. There was a kind of beauty in its disobedience, a geometry too perfect to be natural, too chaotic to be designed. Some called it a rock from another star. Others whispered that it might not be a rock at all. The data spoke in contradictions: brightness without mass, acceleration without thrust, stability without reason. It was as if the object existed in two states at once, real enough to detect, but unreal enough to defy explanation. And so the question arose: what defines the real in science? Is it what fits our equations, or what refuses to? When the instruments are honest, but the universe is not, the meaning of truth itself begins to blur. The astronomers who watched 3-Eye Atlas understood they were witnessing something that did not belong to our solar system, perhaps not even to our understanding of nature. In its silence, in its untraceable origin, it carried the quiet implication of something larger. That reality might still hold secrets it was never meant to reveal. It began, as many discoveries do, not with revelation, but with anomaly. On a quiet night above Hawaii, the Atlas Survey System, a network designed to guard Earth from the sudden approach of near-Earth objects, detected a faint, wandering light. It moved too quickly to belong to any known comet, yet too faintly to be an asteroid. Its path cut across the heavens like a thought escaping gravity. The telescope's sensors recorded its position again and again, each data point confirming what intuition resisted. This was something foreign, something that did not belong to the solar system at all. As more observatories turned their gaze toward it, the equations began to fail. Its orbit was not elliptical, but hyperbolic, the mathematical signature of an interstellar traveler. Only two such objects had ever been confirmed before: Oumuamua in 2017 and Borisov in 2019. Both were strange, but both still obeyed, however loosely, the laws of celestial mechanics. 3-Eye Atlas, however, seemed to disobey everything at once. Its speed suggested an origin beyond any known gravitational influence. Its direction pointed toward no familiar star. It came not from a place, but from an absence, a vector emerging from the uncharted dark between systems. When scientists examined its light, the strangeness deepened. Spectral readings revealed gradients of cyan and pale green colors, uncharacteristic of frozen volatiles or silicate dust. These hues hinted at a surface chemistry unlike any comet observed before. Light curves shifted unpredictably, suggesting that the object's surface was irregular or perhaps layered with materials of varying reflectivity. For a moment, the data hinted at metallic reflection, not proof of artifice, but enough to whisper the possibility. Within days, a silent alliance formed across continents. From Chile's dry peaks to Spain's high plateaus, telescopes tracked its faint pulse across the black. Astronomers compared notes in real time, recalibrating instruments, correcting parallax, questioning their assumptions. Yet every refinement made the mystery sharper. Its spin rate appeared unstable, oscillating faster than any natural body of comparable size could survive. Mathematical models predicted disintegration, but 3I Atlas endured a stubborn coherence against physical expectation. Some proposed that unseen outgassing might stabilize it, as in ordinary comets, but no coma, no visible halo of gas or dust ever appeared. Others suggested that the object's composition might be unusually dense, perhaps metallic. Still, the observed brightness contradicted such density. The numbers cancelled each other out like a cosmic riddle. It was as if 3I Atlas had been assembled to confuse the very principles meant to describe it. The final observation run came just before it slipped into the outer dark, beyond the reach of most instruments. Polarization analysis, a delicate method of studying how light scatters from a surface, returned a final surprise. The reflected light was polarized in a way that suggested either an unusually smooth structure or an engineered symmetry. In other words, its surface was behaving like something designed, or at least something that had once been shaped by forces unlike any in the natural history of this system. For the astronomers who watched its fading trace, the data offered no closure, only a deeper tension. The numbers told a story that reality refused to confirm. The object moved on, silent and indifferent, vanishing toward the constellation of Pegasus. What remained was not proof, but a lingering question, one that stretched far beyond data or theory. If something from another world can pass through ours and defy every rule we know, what other truths might already be drifting unseen between the stars? The data gathered in those few weeks became the focus of months of study. Each new analysis only amplified the confusion. When researchers corrected for atmospheric distortion and telescope motion, the irregularities in brightness persisted. This meant the fluctuations were not observational errors, but genuine, physical changes in the object's surface or orientation. Attempts to model its shape using photometric data suggested a complex, elongated form, possibly tumbling through space rather than spinning on a stable axis. The rotation period appeared inconsistent, changing slightly with every observation window, a sign that something was affecting its movement externally. As the analysis continued, one pattern stood out. The object's motion was subtly inconsistent with predictions derived from gravitational models alone. Small deviations on the order of millimeters per second indicated that some additional force was acting on it. Solar radiation pressure, the gentle push of sunlight, could theoretically account for this if the object were unusually thin or light. But that explanation created new problems. Its brightness and spectral readings did not match the properties of a thin, reflective sheet. The inconsistencies built a case that 3I Atlas was composed of material unlike anything previously catalogued in the interstellar record. Radar and infrared follow-ups were attempted but yielded little. The object's distance and faintness made detailed imaging impossible. The infrared signal was weaker than expected for a cometary body, implying a low level of thermal emission. This meant either that its surface was highly reflective, losing little heat, or that it contained materials with unknown thermal properties. A few teams suggested that its outer layer might include frozen gases mixed with complex carbon compounds, forming a surface that both absorbed and re-emitted energy in unpredictable ways, further complicating the analysis. Its trajectory traced backward through interstellar space, toward no obvious stellar source. Simulations projecting its path suggested it had likely wandered for millions, perhaps billions, of years before entering the solar system. Unlike Borisov, which clearly originated from a nearby star-forming region, the first atlas had no identifiable point of origin. It may have been ejected from a planetary system long since destroyed, or from a small rogue planet drifting through the galaxy. As data was compiled, astronomers debated how to classify it. The International Astronomical Union ultimately maintained its designation as a possible interstellar object, pending more evidence. But within the scientific community, discussions turned to what its properties implied. If the object was natural, it demonstrated physical behaviors that standard cometry models could not explain. If it was unnatural, it would suggest either an artificial construct or a fragment of a process entirely unknown to human physics. Most scientists avoided the second possibility publicly, though it quietly fueled independent research papers, many published through preprint archives like Arxiv. The Atlas team continued refining their data until the signal became too faint to detect. Each updated observation reduced the margin of error, yet none resolved the contradictions. No emission lines corresponding to water, carbon monoxide, or methane, the usual signatures of cometary activity, were detected. Without those, there was no evidence of outgassing or sublimation. The object was dry, inert, and stable, yet still accelerating slightly away from the sun. This inconsistency became one of the most discussed features of 3I Atlas. A small but measurable acceleration without mass loss contradicted Newtonian expectations. The explanation proposed for Oumuamua, radiation pressure from a highly reflective, thin structure, was considered again, but the color data of 3I Atlas didn't align. Its spectral reflectivity showed a neutral to greenish hue, not the reddish tone expected of metallic foil or ice. By the time it left the inner solar system, the first atlas had already become one of the least understood bodies ever recorded. What remained was an incomplete dataset, a few hundred observations across several weeks, thousands of brightness readings, and an open question that no one could close. Astronomers began using statistical models to estimate how many such visitors might pass through undetected each year. The answer suggested that Earth's telescopes capture only a fraction of the interstellar debris that drifts across our path. In the absence of direct observation, attention turned to simulation. Supercomputers attempted to recreate the object's motion, composition, and interaction with sunlight. None produced a stable configuration that matched the recorded data. The final models proposed either a porous, carbon-rich body of extreme irregularity, or something entirely unclassified. Every explanation pointed to the same conclusion. 3I Atlas was unlike any known comet, asteroid, or fragment. When it finally faded from view, its coordinates were logged and archived. A string of numbers and timestamps marking its brief intersection with human observation. For astronomers, it was a reminder of how little the solar system could explain about the galaxy beyond it. For planetary scientists, it became a reference point, a challenge to the definitions that separate what is natural, artificial, or simply unexplained. What remained certain was only this: 3I Atlas had come from elsewhere, had defied the rules that should have described it, and had returned to the interstellar dark without revealing why. In the months that followed its discovery, 3I Atlas refused to behave like anything born of ordinary physics. What was first catalogued as a faint interstellar wanderer began revealing layers of contradiction each observation, unwrapping a deeper mystery. Its light, when measured across wavelengths, carried a signature that belonged nowhere in the known taxonomy of spaceborne matter. Not a comet, not an asteroid, not the frozen shard of a dead world. Its albedo, its ability to reflect sunlight, was too bright in the blue band, too muted in the infrared, and subtly variable, as though its surface shifted in texture or composition between one night and the next. Astronomers called it an albedo out of place, yet behind the sterile phrasing, a quiet unease grew. They were watching an object that did not fit the laws of reflection itself. Even its structure defied ordinary decay. When telescopes captured higher resolution composites, faint threads appeared trailing behind its streams of light and matter that should have dissipated into the void. But they didn't. These fragments seemed to linger, coiling faintly in the wake like vapor refusing to disperse. Some frames suggested that the trails drifted, then converged as if gravity, magnetism, or something yet unnamed was pulling them back together. The behavior was subtle, almost illusory, but the data persisted. In the vacuum, where all things scatter, the first atlas seemed to reorganize itself. Spectroscopic readings deepened the confusion. In early observations, its surface hinted at frozen carbon compounds common to comets and interstellar debris. Weeks later, the same instruments detected metallic resonance, with peaks near nickel and iron lines. Still later, the signature shifted again, now leaning toward complex hydrocarbons. Either the readings were flawed, or the object was undergoing chemical evolution mid-flight. No natural mechanism could fully explain such transformations. Radiation could erode a surface, but not alter its apparent composition across the visible and infrared spectrum so swiftly. Theories emerged suggesting sublimation layers, perhaps ancient, multi-material strata revealing themselves as it rotated. Yet even that failed to explain the faint electromagnetic bursts that flickered intermittently, as though the object itself emitted energy in measured intervals. The rhythm of those flashes was haunting, barely detectable, separated by hours or days, but repeating with uncanny precision. Most dismissed them as random noise, solar interference, or the signature of tumbling rotation. Others noted how the intervals matched neither expected spin rates nor the stochastic behavior of outgassing jets. It was not a signal in the communicative sense, but there was a pattern, a cadence, that made some wonder if it was the byproduct of an internal mechanism, something regulating its energy dissipation. As the mystery unfolded, inevitable comparisons rose to the surface. Oumuamua, the first confirmed interstellar visitor, had rewritten our definitions of what could drift between stars. It too had shown impossible accelerations, slipping past the sun faster than gravity alone could account for, without ejecting gas or dust. But 3I Atlas was worse, less predictable, less compliant with thermodynamic law. Oumuamua had been slender, reflective, and quietly alien in motion. 3I Atlas, by contrast, was chaotic, a tumbling shard whose light refused constancy, whose behavior hinted at processes no model could simulate. It was, as one physicist wrote, a mirror reflecting nothing we know. NASA's deep field tracking soon lost visual contact as the object receded beyond the range of optical systems. What remained were the conflicting datasets, irregular spectra, inconsistent albedo curves, and anomalous photometric pulses. When mapped together, the inconsistencies formed a strange symmetry, as though the object had a design hidden in its disarray. Theorists proposed every natural explanation: fragmented comet core, metallic remnant of a destroyed exoplanet, carbonized crust from a rogue body scorched by radiation, but none matched all the data simultaneously. Every solution explained one behavior while contradicting another, and so the discussion began to shift. Some astronomers suggested that both Oumuamua and 3I Atlas were not singular anomalies, but members of a class interstellar objects shaped by physics beyond our current comprehension. Perhaps these visitors were not random debris, but relics from ancient stellar systems, survivors of collisions that rewrote their chemistry in ways unseen in our own neighborhood. Others speculated more boldly that they could be remnants of engineered matter, fragments of long-lost civilizations, or artifacts of cosmic processes that blur the line between the natural and the constructed. The truth, however, remained beyond measurement. 3. The first atlas had already begun to fade, moving outward past Jupiter's orbit, carrying its enigma into the outer dark. But the data it left behind continued to pulse through the scientific world like an afterimage. It was the kind of mystery that humbles observation itself, the reminder that even the most advanced instruments can only translate light, not the intent behind it. In the endless night between stars, 3. The first atlas drifted on, indifferent, unclassified, and still quietly alive with questions no telescope could yet resolve. As 3I Atlas moved farther from Earth, the international scientific community began consolidating all available data into shared repositories. Teams from NASA, ESA, and independent observatories pooled their results, hoping to reconcile the inconsistencies that had plagued every analysis since its detection. The priority was to determine whether the anomalies were real or products of observational error. Calibration checks were performed repeatedly, spectrometers were cross-referenced, and atmospheric interference models were rerun to rule out instrumental contamination. Nothing explained the variations. The object's spectral signature continued to defy replication under controlled simulations. Infrared readings, in particular, proved most perplexing. Normally, a yen object traveling through the solar system absorbs and re-emits solar radiation in predictable thermal patterns. But 3I Atlas displayed a fluctuating heat emission profile. At times, its surface temperature appeared higher than expected for its distance from the Sun, as if it were absorbing and retaining energy with an unusual efficiency. This led some researchers to propose that it might possess a surface composition capable of dynamic albedo adjustment, similar in principle to adaptive materials being developed on Earth, but on a vastly larger and older scale. Others rejected this outright, suggesting it could simply be an irregular rotation that exposed darker and lighter surfaces at different angles. Yet even these models failed to match the frequency of variation. Observed another area of investigation centered on its trajectory. Early orbital models indicated a standard hyperbolic path consistent with an interstellar origin. However, subtle deviations emerged as more precise tracking data became available. While still within the bounds of statistical uncertainty, the deviations persisted across multiple independent datasets. If accurate, they suggested a minor but measurable acceleration component, one not easily attributed to solar radiation pressure or gravitational interactions. This small inconsistency reignited debates first triggered by Oumuamua's unexplained acceleration. Could both objects share a common propulsion mechanism unknown to current physics? The study of polarization data added further complications. When sunlight reflects off surfaces in space, it becomes polarized in characteristic ways depending on texture and composition. The degree of polarization observed from 3I Atlas exceeded what would be expected from typical cometary dust or rocky material. Instead, it suggested either a surface composed of highly ordered crystalline structures or one covered by a fine layer of metallic compounds. Laboratory attempts to reproduce similar polarization patterns yielded inconclusive results. Even under idealized conditions, no known material combination matched the recorded values exactly in response. Theoretical physicists began exploring broader frameworks. Some proposed that 3I Atlas might be composed of exotic matter formed under extreme astrophysical conditions. such as those near neutron stars or within supernova ejecta. These scenarios could, in theory, account for its resilience and anomalous reflectivity. However, they also implied a formation environment far removed from any star system currently mapped. Others suggested that it might be a fragment of a larger body, one that experienced catastrophic disassembly long before entering our system. The lack of detectable debris fields along its inbound trajectory, though, made this difficult to verify. By the time it crossed Saturn's orbital distance, the object had dimmed beyond most optical instruments' capabilities. Only the largest observatories, using advanced adaptive optics and radio tracking assistance, could still detect its faint presence. Each observation became a struggle against noise, yet the scientific drive to gather data remained strong. Every remaining signal mattered, not for confirmation, but for continuity. 3I Atlas had become more than an astronomical target. It was a test of how far observation could stretch before giving way to speculation. In academic circles, papers began to appear proposing frameworks for a new class of interstellar anomalies. Theories suggested that such objects could represent transitional matter, fragments from planetary systems disrupted by stellar migration or black hole interactions. These remnants, shaped by forces unlike those found in stable systems, might naturally exhibit irregular optical and chemical properties. Though speculative, the model offered one of the few explanations that fit multiple data points simultaneously. Still, even these attempts stopped short of offering certainty. As data collection waned, simulation replaced observation. High-performance computing centers reconstructed every known parameter: rotation, light curve, polarization, heat profile, to project its likely future state. Most models concluded that 3I Atlas would eventually drift into the outer Earth-like regions of interstellar space, its velocity ensuring it would never return. Its mystery would remain unresolved, preserved only in datasets and archived spectra. What the object truly was, a natural fragment, a remnant of cosmic extremities, or something altogether unknown, remained outside the reach of current science. The evidence was real, but incomplete. What persisted was the question: how many more of these objects traversed the galaxy unseen, carrying the same quiet defiance of explanation? Long before the digital era of automated telescopes and global sky surveys, humanity's relationship with the heavens was one of awe and limitation. For most of recorded history, every point of light that drifted across the sky was assumed to belong here, bound to the sun's gravity, part of the cosmic neighborhood that shaped the rhythm of night and day. The comets that blazed briefly through the firmament were seen as omens, their origins mysterious but never foreign. Even as Newton revealed the laws of celestial mechanics, and Kepler charted the invisible geometries of orbit, the assumption endured: everything that moved around us was part of the same system, born from the same disk of ancient dust. The cosmos, vast as it was, still seemed to obey a comforting boundary, one that kept the solar system, contained. That illusion lasted until 2017, when a slender shard of something unexpected crossed the lens of the Pan-STARRS telescope in Hawaii. Its light curve flickered irregularly. Its trajectory was steep and fast, too fast for a native object. This was Oumuamua, the first confirmed interstellar object ever recorded by humankind. It entered the solar system unannounced, tumbling end over end, accelerating slightly as if under an unseen force. For astronomers, it was the first tangible evidence that the void between stars was not empty but alive with travelers, fragments, remnants, perhaps even messengers from distant systems. Oumuamua was small, dark, and silent, yet it opened a door that had remained closed for 4.5 billion years. The solar system, once thought to be isolated, had just been reminded of its place in a galactic current. 2 years later, the skies revealed a second visitor. This one, designated to I, Borisov, was unmistakably cometary, surrounded by a halo of vaporized ice, expelling gas and dust in the familiar language of solar heating. Unlike Oumuamua, Borisov obeyed the models. It was, in every measurable way, a natural interstellar wanderer. Its behavior confirmed that the first detection was no fluke. Interstellar visitors existed, and our instruments had finally become sensitive enough to notice them. But even as Borisov drifted back into the darkness, astronomers knew that these events were rare, perhaps once in a decade, perhaps once in a century. The instruments were watching, waiting for the next anomaly. By 2024, the Atlas Survey System, an automated network of telescopes scanning the night sky for transient events, was operating at peak sensitivity, designed to detect hazardous near-Earth asteroids. It constantly mapped faint streaks of light against the background of stars. The software flagged movement, anything that didn't align with known orbital paths. It was here that an unassuming entry appeared, a faint moving point, catalogued briefly, then examined more closely. Its motion was strange, its speed higher than expected, its brightness variable. The team cross-referenced its trajectory against orbital models, and the conclusion emerged almost immediately: hyperbolic, inbound, and unmistakably foreign. The object was assigned a provisional name, 3I Atlas, the third confirmed interstellar object ever observed. The scientific world was ready this time. Within hours, observatories across the planet were redirected to the coordinates. From Hawaii to Chile, from the Canary Islands to the South African Astronomical Observatory, telescopes synchronized their focus. Unlike with Oumuamua, where initial confusion led to a brief observational window, 3I Atlas was tracked from the moment of detection. Its light curve, its color, its changing motion, all recorded with precision. But as the data accumulated, something subtle began to disturb the certainty that had been gained through previous encounters. The readings did not align with any known pattern. Its brightness fluctuated irregularly, as if it were rotating along multiple axes or composed of reflective materials inconsistent with rock or ice. The early assumption that it was another natural interstellar comet began to weaken. Behind these observations lay the instruments themselves, the silent machines of human curiosity. The Atlas telescopes, designed primarily as planetary defense tools, had become instruments of cosmic discovery. Paired with systems like Pan-STARRS, the Vera Rubin Observatory, and the European Space Agency's Gaia mission, they formed a global network that transformed the night sky into a continuous record of motion. Every hour, they captured terabytes of light data, translating photons into coordinates, magnitudes, and probabilities. It was through this seamless web of observation that 3I Atlas had seen a faint pulse of light that might otherwise have gone unnoticed, but the lineage of such discovery stretches back far beyond silicon and sensors. It reaches into the era of glass and brass, when Galileo first turned his crude telescope toward Jupiter and saw the dance of its moons, proof that the heavens themselves were dynamic. It flows through the hands of Caroline Herschel, William Parsons, and Edwin Hubble, whose patient observations turned the infinite from myth into measurable expanse. Each discovery extended the horizon, each refinement in optics and mathematics peeling back another layer of cosmic silence. The instruments evolved, but the impulse remained unchanged: to know what lies beyond. When 3I Atlas entered the story, it did more than add a third entry to a growing list of interstellar wanderers. It marked a turning point in the narrative of observation itself. Humanity had spent centuries refining its ability to see the sky, to isolate the faintest signatures of motion from the noise of eternity. But what the telescopes revealed this time was not clarity, it was contradiction. The better the instruments became, the stranger the universe appeared. The more precise the measurements, the less the object seemed to conform to known physics. In this way, 3i Atlas became both a triumph of detection and a reminder of limitation, a silent messenger from a domain that refuses to explain itself. Every photon collected by those instruments carried with it a trace of something ancient and untranslatable. Across continents and time zones, the data streamed through fiber networks and satellites, converging into global databases. Teams of scientists logged in to analyze brightness curves, model trajectories, compare reflectivity profiles. Some saw in its behavior echoes of chaos, a relic torn from a dying world. Others saw symmetry, hints of intention, of structure too ordered to be coincidence. Between these interpretations lay the unbroken thread of scientific humility. That discovery does not always mean understanding. And so, the origins of the 3i Atlas discovery tell two stories at once. One is technological, a chronicle of instruments, algorithms, and collaboration across the planet. The other is human, a continuation of that same ancient curiosity that once drew stargazers to chart constellations with nothing but naked eyes. Together they culminated in a moment when the universe revealed something new, not to be explained, but to be noticed. For a brief span of weeks, all the precision of modern astronomy turned toward a single moving point, carrying with it a truth both exhilarating and humbling, that even after centuries of looking upward, the cosmos still holds phenomena that do not fit within the framework of understanding visitors from beyond, whose very existence reminds us how much remains unseen. As the data from the initial detection of 3i Atlas stabilized, analysis shifted from excitement to verification. The discovery teams worked through the standard confirmation process, checking cross-observations, recalibrating instruments, and validating timestamps against satellite tracking. Nothing in the early dataset suggested error. The signal-to-noise ratio was high, the trajectory consistent, and the movement distinct from known orbital debris. What stood out was the object's apparent reflectivity, which exceeded that of typical carbon-rich or silicate-rich asteroids. Its albedo placed it in a narrow range associated with highly reflective alloys or crystalline structures. Yet no known natural process in interstellar space was expected to produce an object with such sustained brightness across multiple observation windows. Within days, the International Astronomical Union officially designated its 3i Atlas, confirming its hyperbolic orbit. The orbital eccentricity value greater than uneliminated any possibility of a gravitationally bound path. In practical terms, that meant the object would visit the solar system once and never return. Its inbound velocity exceeded 30 kilometers per second relative to the Sun, similar to, but not identical with that of Almor. These measurements placed it firmly in the category of interstellar visitors. Yet its optical behavior did not align with either of its predecessors. It was moving like a fragment of rock, but shining like refined metal. The follow-up observations from the Very Large Telescope in Chile and the Gemini North in Hawaii expanded the dataset. Spectroscopic readings identified faint absorption features that did not match the signatures of common volatiles like water, carbon monoxide, or ammonia. Instead, the spectrum contained broad, reflective plateaus suggestive of complex silicate compounds, mixed with unknown reflective materials. When temperature models were applied, they produced conflicting results. Surface heating from solar radiation did not correspond to expected sublimation rates. The object appeared inert, lacking the gaseous outflows typical of comets, yet still showed variable brightness patterns. At NASA's Jet Propulsion Laboratory, teams ran orbital simulations backward to estimate the origin trajectory. The models pointed toward the region of the constellation Lyra, but the margin of error spanned tens of light-years. Even with advanced gravitational modeling, identifying the parent system was nearly impossible. Over interstellar distances, gravitational perturbations from multiple stars distort any traceable path. What the simulations confirmed, however, was that the object entered the solar system from above the ecliptic plane, approaching from an angle inconsistent with typical interstellar drift. That trajectory implied a complex dynamical history, possibly influenced by multiple stellar flybys or ejection from an unstable system. Data from radar mapping attempts proved inconclusive. The signal was too faint, the object too distant for meaningful surface resolution. Nonetheless, early photometric analysis suggested a highly elongated body, potentially hundreds of meters long but only a fraction as wide. This shape recalled Oumuamua's unusual dimensions, but the light behavior hinted at a smoother or denser surface. That distinction became a focal point in academic debate. If 3I Atlas were dense and cohesive enough to maintain such a structure while traversing interstellar space, it must be composed of materials resistant to both thermal erosion and micrometeorite impacts accumulated over millions of years. Parallel research efforts examined archival sky survey data to determine whether the first atlas had been detected previously at fainter magnitudes. Analysis of Pan-STARRS and Gaia archives found no earlier record, suggesting it was first visible only after crossing the outer boundary of the solar system. This supported the theory that the object's surface properties changed under solar radiation, possibly activating a reflective layer or releasing volatiles trapped beneath its surface. Yet, despite this hypothesis, no tail or coma was detected, even under deep exposure imaging. By the third week after detection, data sharing became standardized under coordinated observation networks. Automated telescopes continued tracking while astrophysicists ran comparative studies with Borisov and Oumuamua. The inconsistencies deepened. Unlike Borisov, which displayed predictable mass loss behavior, and unlike Oumuamua, which accelerated anomalously, 3I Atlas appeared stable in velocity but unstable in light output. It neither accelerated nor decelerated beyond gravitational expectation, yet its brightness curve shifted unpredictably. The pattern was not random, it oscillated within definable intervals, but no known mechanism explained the sequence. The broader implications became clear. 3I Atlas demonstrated that interstellar visitors are not a single class of objects, but a diverse category of phenomena, possibly representing multiple formation processes across the galaxy. Each carried different clues about stellar system evolution and material diversity. The discovery underscored how limited human understanding remains when confronted with objects that do not adhere to known cosmic patterns. The deeper astronomers looked, the clearer it became that 3I Atlas could not be fully explained within existing astrophysical models. The next phase of investigation would not focus on where it came from, but on what it was: composition, structure, and the physical principles that allowed it to exist intact across the vacuum between stars. In the quiet hours of the observatories, long after the last calibration had been checked and the instruments left to track their silent visitor, a different kind of storm began to form, not in the sky, but in the minds of those who had seen the data. What 3I Atlas represented was not merely a discovery, but a confrontation with uncertainty. The numbers did not align, the models resisted interpretation. and the implications stretched uncomfortably close to the boundary between science and speculation. Inside research facilities and digital meetings across continents, the same question hung in the air. What if this object truly was something that should not exist? At first, skepticism reigned. Some dismissed the readings as optical interference. Others pointed to instrument drift or data misalignment. The brightness fluctuations could be compression artifacts. The polarization data could have been skewed by atmospheric refraction. In the world of empirical science, extraordinary claims demanded extraordinary caution. The community had lived through this tension before. The lingering echoes of Al-Murmur still haunted academic corridors. That object had also defied classification, and when a handful of researchers suggested artificial origins, reputations were quietly bruised. Careers built on precision and restraint found themselves entangled with media sensationalism. No one wanted to repeat that cycle. Still, the data would not conform. Night after night, astronomers reran their analyses, recalibrated their sensors, compared readings from independent observatories thousands of kilometers apart. The results remained consistent. The object's reflective patterns, its lack of cometary tail, the irregular but persistent spectral shifts, all pointed toward something genuinely unorthodox. A small circle of astrophysicists began to argue that the object's properties were statistically significant, enough to merit publication. Others advised patience, warning that early interpretation could damage credibility if proven wrong later. What emerged was a quiet standoff between belief and evidence, between the intellectual courage to follow data wherever it led, and the professional instinct to guard against error. The tension was compounded by time. 3I Atlas was fading fast, its outbound trajectory carrying it beyond the reach of most telescopes. Observing windows narrowed with each passing night. Every hour lost meant another dataset slipping into darkness. Proposals were drafted for emergency observation time on major facilities, Hubble, Gemini, Subaru, but approval required justification, and justification required consensus. Without agreement on the object's importance, funding agencies hesitated. In the bureaucracy of science, even cosmic mysteries had to pass through committees. For some researchers, it was a painful reminder that curiosity alone was never enough. Discovery demanded permission. Within these pressures, the human side of science began to surface. The late nights grew longer, the coffee colder, and the conversations quieter. Many of the astronomers involved were veterans of deep space surveys, individuals accustomed to patience and uncertainty. Yet even they felt the growing strain of contradiction. The data was extraordinary, but the implications felt dangerous. Some feared that open discussion could trigger another wave of speculative media attention, the kind that dilutes serious inquiry into sensational soundbites. Memories of headlines declaring alien spacecraft detected during the Oumuamua debate lingered like scars. The line between exploration and entertainment had blurred, and few wanted to find themselves standing on it again. Despite their caution, the leak came. A journalist monitoring data repositories noticed the unusual pattern of telescope time requests linked to the Atlas detection and began to inquire. Within days, early details appeared online. The phrasing was familiar. Unidentified object exhibits non-natural properties. Headlines multiplied. Interpretations grew louder, and social media lit up with claims of interstellar technology and alien reconnaissance. Scientists who had spent months choosing every word of their internal reports with surgical precision now watched. Those same findings transformed into viral speculation. For a field defined by careful validation, this was chaos. Public fascination brought attention, but it also distorted context. Some institutions issued cautious statements emphasizing the natural explanations still under review, while others chose silence, preferring not to feed the frenzy. Meanwhile, data analysts, still working behind the scenes, pushed ahead despite the noise, filtering through the last fragments of usable telemetry. Many of them knew that by the time the public's excitement faded, 3i Atlas would already be gone, its secrets locked behind light years of separation. In those final days of observation, something shifted. The debate that had divided researchers softened, replaced by a quieter recognition. Whatever the object truly was, it had forced a confrontation with the limits of current understanding. Whether natural or something beyond, its presence had rekindled a deeper truth. Science advances not by certainty, but by enduring curiosity in the face of the unknown. The discomfort, the disagreement, even the public misunderstanding, all of it was part of the same human struggle to comprehend a universe that rarely offers closure. When the last light signature faded from the screens and the data streams went silent, the researchers were left not with answers, but with questions that reached beyond measurement. The pursuit had cost time, energy, and peace of mind, but it had also reaffirmed something essential: that discovery is not only about what is found, but what it asks of those who seek it. 3i Atlas had not just tested their instruments, it had tested their faith in reason itself. In the long arc of scientific history, such moments define the boundary between what humanity knows and what it is willing to imagine. And that, more than any dataset, is where discovery truly begins. As the days turned into weeks, the echoes of 3i Atlas continued to ripple quietly through the global scientific community. The object itself was long gone, its trajectory slipping into interstellar darkness, but its imprint on the minds of those who studied it remained vivid. The archived data was dissected again and again: brightness curves, radial velocities, polarization maps, each parameter subjected to relentless scrutiny. Yet, the numbers remained stubbornly indifferent to human expectation. There was no simple error, no overlooked calibration flaw. What they had observed was genuine, and that authenticity made it all the more troubling. Behind closed doors, committees began drafting the first official papers. Language became their new battlefield. Every sentence was weighed for caution, every adjective debated. Words like anomalous or unexplained carried scientific risk. They invited speculation, potentially jeopardizing credibility. The result was prose stripped of emotion, wrapped in restraint. Yet, beneath those careful phrases lay a quiet admission. This object did not behave like any natural interstellar body previously observed. Its shape and albedo ratios defied easy modeling, and its tumbling motion hinted at a complex, possibly hollow geometry. The more they tried to describe it, the more elusive it became. In the process, an unspoken fatigue settled in. The researchers who had once felt the thrill of discovery now carried the weight of interpretation. Each new analysis opened another layer of ambiguity. Statistical models yielded probabilities, but no certainty. Even among teams that disagreed, there was growing respect for the enormity of the unknown. The debates had cooled into contemplation. For some, that uncertainty was unbearable. For others, it was precisely what made science worth pursuing. Funding agencies, meanwhile, reacted with their usual rhythm: cautious, procedural, pragmatic. Proposals for follow-up missions were filed, reviewed, and delayed. The justification for a new interstellar object surveillance network was discussed in the shadow of limited budgets and competing priorities. Space agencies considered revising their early warning algorithms to better capture similar fast-moving targets in the future. Every system, it seemed, was adapting to a new reality. The solar system was not isolated. And these visitors were no longer theoretical. Within research institutions, a subtle cultural shift began to take shape. Younger scientists, unburdened by the reputational scars of past controversies, felt emboldened to ask harder questions. What if interstellar objects were more common than previously assumed? What if their diversity extended beyond natural formations? Could some carry relics, material or structural, from civilizations long extinct? These were not conclusions, but possibilities whispered in corridors after hours, when the fear of ridicule was low and curiosity could breathe freely. Outside academia, the noise of public discourse began to fade. Media interest drifted toward new headlines, and the frenzy surrounding 3i Atlas settled into the slow rhythm of documentary retrospectives and quiet online discussions. Yet, for the astronomers who had lived through it, the silence felt incomplete. Many continued to revisit the datasets in private, running new simulations and refining models. Some published cautious addenda months later, updating values but never revising the core mystery. The object's nature remained unresolved, but its influence endured. It had expanded the perimeter of what could be asked. The emotional aftermath was subtler but no less real. Some scientists, privately, admitted to sleepless nights, not from pressure, but from the gravity of what they might have glimpsed. For decades, astronomy had trained them to interpret light as a language, every photon a message from some distant process. With 3i Atlas, that language had momentarily become unfamiliar. It reminded them that observation is not only a technical act, but a philosophical one. To look into space is to confront the limits of human perception, to acknowledge that some truths may not fit within existing frameworks. Years later, when the official records of 3i Atlas were compiled into archives, the raw data was preserved alongside the meeting notes, email exchanges, and observation logs. Together, they told a story not only of detection, but of confrontation between evidence and expectation, reason and imagination. The discovery had not rewritten physics, but it had redrawn the emotional boundaries of science. It showed that even in an age of precision instruments and machine learning, discovery still carried human weight, the hesitation to speak, the courage to question, and the quiet awe before the unexplained. In the end, 3i Atlas became more than an interstellar traveler. It became a mirror reflecting the minds that sought to understand it. Its departure left behind not closure, but a deeper commitment to the pursuit itself. The astronomers, scattered across observatories and institutions, eventually moved on to other projects, yet the memory lingered. Somewhere beyond the reach of their instruments, that fragment of another world continued its silent journey between the stars, indifferent to the debates it had sparked, yet eternally tied to the moment humanity first noticed it passing by it first. 3i Atlas seemed easy to explain. The simplest theory always comes first, the comet hypothesis. A small, icy traveler, perhaps ejected from the outskirts of another star system, making a rare and beautiful pass through ours. But as telescopes followed it, frame by frame, the illusion began to dissolve. There were no jets of vapor, no faint trails of sublimating ice, no tail stretching into solar light. Its motion was silent, clean, almost sterile. The infrared readings that should have revealed escaping volatiles returned nothing. It behaved like a comet without the breath of one, a ghost of a category that no longer fit. Next came the asteroid theory, a fragment of rock, perhaps metallic, glinting as it rotated under the distant light of the sun. Its high reflectivity, or albedo, seemed to confirm it. Yet, when mass estimates were run, the numbers refused to cooperate. The object was too light for its apparent brightness. A rock that bright should have weighed more, resisted solar radiation more forcefully. Instead, 3I Atlas accelerated in subtle but measurable ways, as though pushed by something unseen. Radiation pressure alone could not account for it. The same unexplained behavior that once puzzled astronomers with Oumuamua had returned, more exaggerated, more deliberate. Some sought comfort in more exotic origins. One proposal suggested the 3I Atlas might be a fragment from a dying star, a shard cast off during a supernova's chaotic final exhalation. Such fragments could, in theory, travel between stars, carrying the elemental signatures of their birth. But when teams ran the velocity vector backward through stellar charts, nothing matched. No recent supernova, no remnant cloud, no traceable source in the galactic neighborhood aligned with its path. If it was a messenger, it came from nowhere that human instruments could name. The gaps between explanations widened, and into that silence came the most divisive question of all. Some dared to ask whether it was natural at all. The phrase alien artifact reappeared, whispered first, then published cautiously in op-eds, papers, and podcasts, not as a claim, but as a question. Could 3I Atlas be a relic, a probe, or a remnant of something constructed? The thought echoed through the same channels that once carried the Oumuamua bait, reigniting the unease between curiosity and credibility. For every scientist who argued against such speculation, there was another who quietly admitted that the data didn't rule it out. Its brightness pattern was consistent with flat, reflective surfaces, not entirely unlike metallic panels. Its polarization readings hinted at order, not randomness. Yet, no one could identify a definitive signature of artificial design. It was a possibility trapped between science and philosophy, between data and doubt. As the controversy grew, teams across the world began to re-examine every line of data. Calibration routines were rewritten, instruments checked for optical distortions, algorithms rerun on archived observations. From Hawaii to Chile, from space-based telescopes to ground observatories, the results converged. Nothing was wrong with the instruments. Every measurement confirmed what the others had seen. The readings were consistent, the uncertainty statistical, not procedural. The object's behavior was real, not illusion. Then came the pause. For months, papers slowed. Observatories moved on to other targets, not because the mystery was solved, but because it had reached a kind of scientific paralysis. Every new idea circled back to the same unanswered questions. Without fresh data, theories began to feel like echoes. Conferences held quiet panels on 3I Atlas, but few spoke with confidence. Those who had followed it longest described the feeling not as frustration, but as reverence, the acknowledgement of something genuinely beyond current comprehension. In the silence that followed, the story of 3I Atlas shifted from discovery to reflection. It became less about what it was and more about what it represented, a reminder that not all phenomena yield to immediate explanation. Even with the most advanced instruments, even with global collaboration, there remain events that defy the collective intellect of the species observing them. The search did not end in failure. It ended in humility. The first atlas left behind a scar of fascination, a question written into astronomical history. Its path through the solar system was brief, but its impact stretched far beyond its physical presence. It challenged definitions, destabilized certainties, and forced science to confront its own limits. When it finally faded into the cosmic dark, what lingered was not the image of a comet or an asteroid, but a shape without a name, an object that carried with it the unsettling truth that even now, the universe still holds surprises that refuse to fit within the vocabulary of the known. As the scientific community absorbed the silence left by 3I Atlas, the early investigations began to undergo a quiet evolution. The first stage of the process was internal, a re-examination of methodology. Astronomers at the University of Hawaii, Caltech, and the European Southern Observatory started reconstructing the object's path using newly refined orbital integration software. These recalculations, meant to eliminate even the smallest observational error, only reinforced the same improbable conclusion. 3I Atlas was indisputably interstellar. Its incoming speed of over 30 kilometers per second relative to the Sun exceeded any gravitationally bound trajectory. It had not been perturbed from the Oort cloud or the Kuiper belt. It had entered from deep space, carrying with it the chemical and dynamical fingerprints of another star system. This realization brought the focus back to its composition. If it was truly alien to the solar system, then its materials might reveal the conditions of its home environment. Spectral analyses attempted to decode this, but the data proved inconsistent. Observatories detected a combination of silicate reflection and metallic emission lines, but their ratios fluctuated with each pass. Some nights, its spectrum resembled carbonaceous asteroids. Other nights, it suggested nickel-iron content. Such volatility was nearly impossible for an inert rock, suggesting either an active surface process or an internal energy source that altered reflectivity. Yet no corresponding temperature changes were observed in its thermal emissions. NASA's Infrared Telescope Facility and the Gemini Observatory both attempted to capture high-resolution thermal data to measure heat signatures across its surface. The readings came back colder than expected, inconsistent with any active outgassing or internal heating model. If it were venting material, as a comet would, it should have shown infrared spikes. It did not. If it were metallic, solar heating should have induced subtle thermal gradients. It did not. It appeared inert but alive, reacting, shifting, reflecting, yet betraying no physical mechanism to explain it. The European Space Agency's Gaia mission, known for its precise measurements of stellar motion, was brought into analysis. Its data helped refine the inbound vector of 3I Atlas to a small patch of sky near the constellation Sculptor, but tracing it beyond that region led to nothing identifiable, no known star system, no recent ejection event, no gravitational disturbance that could have launched such an object. In the cosmic ledger of motion, it seemed to appear from statistical emptiness. As these findings accumulated, the conversation turned to what could not be seen. Several research teams began to explore the possibility of non-gravitational forces, not radiation pressure, but something else. Some speculated that electromagnetic interaction with interstellar plasma might produce subtle thrust effects. Others suggested a hollow or porous structure, allowing sunlight to impart acceleration without visible heat. A few even explored the exotic possibility of light sail physics, though none could justify how such an engineered design could survive eons of interstellar exposure. Amid these competing interpretations, a crucial observation emerged: the polarization of its reflected light. The way it twisted and scattered photons was not random. Normally, light from tumbling asteroids fluctuates irregularly, reflecting off uneven terrain, but the polarization pattern of 3I Atlas displayed consistency across multiple wavelengths. That implied a geometry that was not chaotic. If it was natural, it was unnaturally organized. If it was artificial, it was inexplicably ancient. Despite the rising tension, the discourse remained grounded in the principles of verification. Peer reviewers demanded caution. Data archives were reopened. Simulations were replicated by independent teams using different software and instrumentation. The same conclusions returned each time: an interstellar object with contradictory physical traits. showing neither the thermal characteristics of ice nor the density profile of rock. By early 2025, the data window had closed. The object's faintness and velocity pushed it beyond the reach of even the largest telescopes. What remained were petabytes of observational data, light curves, spectra, trajectories, each pointing toward the same unresolved narrative. Papers began to emerge summarizing the investigations. The consensus was careful but honest. 3I Atlas did not conform to existing models of natural interstellar debris. The phrase unknown category began appearing in the literature, a classification born not from discovery, but from the inability to define. As the story settled into the archives of astronomy, the deeper question began to take form, not of what 3I Atlas was, but of what it forced science to confront. The early investigations had done their work. They had proven the limits of measurement, the fragility of assumptions, and the persistence of mystery in an age defined by precision. What began as a straightforward detection had ended as a philosophical crossroad. Between the numbers and the silence of space, 3I Atlas had introduced a subtle but enduring message that even in a universe mapped by mathematics, there are still objects that refuse to belong anywhere at ULAT, the farthest edges of measurable science. 3I Atlas began to demand explanations that stretched beyond the comfortable boundaries of known physics. The data spoke clearly enough. Its motion was not random, its light not easily defined, and its passage through the solar system defied classical mechanics in subtle but undeniable ways. It slowed, not abruptly, not dramatically, but with a measurable deviation from the predicted trajectory. In celestial mechanics, even a deviation of fractions of a meter per second is enough to unravel a model. Here, that small hesitation became the fulcrum of an entire mystery. The deceleration did not fit the expected pattern of gravitational influence or solar radiation pressure. There were no visible jets of gas or dust to explain the change in velocity. It was as if the object had interacted with something unseen, a medium or a force not accounted for in any equation. One emerging idea centered on the concept of quantum reflectivity, a hypothesis so far from classical physics that it bordered on speculative. The premise was simple in language, but complex in implication. Perhaps the surface of 3I Atlas interacted with photons in a way that distorted measurements of its motion. If its outer layer was composed of a material capable of reflecting light at varying quantum states, meaning the phase and energy of incoming light waves were subtly altered, then the observed trajectory could be an illusion of data. Yet, this explanation faced an obstacle. Such quantum behavior requires highly ordered structures at atomic scales, the kind found only in engineered materials or crystalline arrangements far more refined than those seen in naturally formed rocks. Other researchers proposed a more gravitationally rooted theory, what they called gravitational memory in general relativity. Space-time curves not only in response to mass, but can retain the influence of mass long after an object has passed through it. If 3I Atlas had crossed regions of deep gravitational distortion near neutron stars, black holes, or collapsed stellar remnants, it might carry a lingering effect, a residual curvature encoded in its momentum. This idea suggested that the object's path was not solely determined by the gravitational fields it encountered here, but also by those imprinted upon it long ago, across light years of interstellar travel. The mathematics of such memory were theoretical, but the concept hinted at a profound truth. The universe might not let go of what passes through it. Another line of investigation examined the physical toll of interstellar weathering. An object traveling for millions of years between star systems would experience forces unknown to local matter. Cosmic rays, high-energy protons, and micrometeoroid impacts would continuously alter its surface. Over eons, such bombardment could transform the molecular bonds of its materials, creating new compounds that cannot exist in planetary environments. Laboratory simulations at NASA's Ames Research Center demonstrated that long-term radiation exposure can produce carbon-nitrogen lattice, structures that mimic organic chemistry yet remain entirely inorganic. If 3I Atlas was covered in such materials, its spectral behavior might appear alive, shifting colors and reflectivity without any biological process. It would not be alive, but it would behave as though it were. Still, the most perplexing evidence remained its trajectory. Some astrophysicists began calling it non-Newtonian motion, a term borrowed from fluid dynamics, where materials can behave unpredictably under stress. In the vacuum of space, nothing should behave this way. Yet, when plotted frame by frame, 3I Atlas appeared to execute minute course corrections, not enough to suggest control, but too coordinated to dismiss as random. The object's path around the sun resembled a deliberate arc rather than a passive curve. Some argued that relativistic drift, a combination of rotational precession and gravitational time dilation, might create the illusion of intent. Others considered the possibility of asymmetric mass distribution within the object, where dense cores or cavities caused its spin to modulate under solar influence. Every hypothesis carried merit, yet none could satisfy all observations simultaneously. As weeks turned into months, the limits of instrumentation became undeniable. Even the most advanced ground-based telescopes and orbiting observatories reached the edge of their capability. The object was too small, too dim, and too distant. Each new image contained less detail, each spectrum more noise. The scientific method found itself confronted not by error, but by the sheer vastness of the unknown. The first atlas existed in that rare category of discovery that sits precisely at the boundary between what can be observed and what must be inferred by this stage. The debate within astrophysics had shifted from data analysis to ontology, the nature of existence itself. Was it more responsible to define 3I Atlas as an unclassified natural object, or to admit that it might represent a phenomenon not yet understood by human physics? The question mirrored similar inflection points in the history of science: the discovery of quantum mechanics, the birth of relativity, the first detections of dark matter. Each had begun with something that refused to fit the model. The first atlas joined that lineage, not as proof of anything extraordinary, but as a reminder that even at the highest resolutions of knowledge, the universe continues to conceal more than it reveals. And so, it drifted outward once more, crossing the invisible boundary where sunlight weakens and instruments fail. The data ended, but the implications did not. In the cold archives of observatories around the world, its traces remain numbers, plots, and spectra, each a small defiance against understanding. The object may have left the solar system, but the questions it raised would linger at the very edge of science, where certainty dissolves into speculation, and the pursuit of truth becomes indistinguishable from the search for meaning itself. As the data from 3I Atlas was finalized and archived, the discussions surrounding it shifted from the observational to the theoretical. The object had long since vanished from view, but its numerical imprint, the coordinates, the light curves, the thermal readings, continued to be analyzed. In research facilities across the world, scientists began constructing models to test new forms of motion that could explain the recorded anomalies. Most of these models started with accepted principles: gravitational influence, solar radiation pressure, or mass ejection, but each failed to align perfectly with the data. The deceleration, the polarization of reflected light, and the absence of visible debris could not coexist under any known physical law. Something about the mechanics of this object challenged the coherence of existing frameworks. A working group within the International Astronomical Union proposed a new analytical approach. Instead of treating 3I Atlas as a discrete object, it should be viewed as part of an interstellar process. This shift in perspective implied that the object might represent a fragment of a larger mechanism, perhaps debris from an ancient collision or a structure ejected from a system undergoing extreme gravitational stress. The team began comparing its trajectory and velocity profile with computational models of tidal ejection from binary stars. Some simulations showed that fragments expelled during the collapse of close stellar pairs could achieve velocities consistent with interstellar travel. However, the material composition predicted by those models did not match the observed reflectivity or color gradients of 3I Atlas. Parallel research emerged in the field of plasma astrophysics. A few researchers hypothesized that the object's surface could have undergone charge separation, the accumulation of static or plasma fields as it interacted with interstellar medium. Over millions of years, such exposure might alter how light interacts with its surface, producing polarization effects similar to those seen in metallic or crystalline materials. This could, in theory, create the illusion of design without requiring any artificial origin. Yet this explanation required a degree of long-term stability that seemed improbable. Charged surfaces tend to discharge in solar environments, especially under the influence of solar wind. For 3I Atlas to maintain consistent polarization patterns, its structure would have to be unusually resistant to electrical dissipation. Meanwhile, quantum physicists began exploring even more abstract possibilities. One paper from the Arxiv preprint server suggested that the object could be exhibiting effects of quantum decoherence at macroscopic scales, that its rotation and reflectivity patterns might represent interference between quantum states, influenced by its long interstellar journey. While this remained highly theoretical, it pointed toward the same central issue. The known laws of motion and light interaction could not account for the observations. As the months progressed, the conversation increasingly turned to the limitations of observation itself. Telescopic systems, even the most advanced, rely on indirect inference, light and time acting as intermediaries between observer and object. Every measurement is subject to interpretation. Calibration errors, atmospheric distortions, and instrumental noise all leave traces that can mislead analysis. Teams revisited the raw data from the Atlas and Pan-STARRS systems to test for these factors. None were found sufficient to explain the anomalies. In the end, the recorded readings were validated independently by observatories using different instruments on different continents. The conclusion was that the anomaly was real. By late 2025, the search for a definitive theory had expanded into cross-disciplinary collaboration. Astrophysicists, chemists, materials scientists, and even aerospace engineers contributed models. Some suggested it could be a fragment of a Dyson-like structure, a hypothetical megastructure orbiting a distant star. Others preferred more conservative explanations, suggesting it might be a remnant of a planetesimal ejected before the formation of a stable solar system. Yet even these natural models required conditions so rare that they bordered on improbable. In the end, what emerged was not an answer, but a boundary. The case of 3I Atlas demonstrated how far human understanding could be stretched before reaching its limit. The physics that governed planetary orbits, star formation, and interstellar motion had no clear solution for this object. It did not violate the laws of nature outright. It simply existed at their margins. where equations lose precision and certainty, becomes conditional. The final consensus papers, published by NASA and the European Southern Observatory, reflected this tension. They concluded that 3I Atlas remained an unresolved interstellar body exhibiting non-compliant physical characteristics. The language was careful, clinical, and deliberate, an acknowledgement of the unknown without surrendering to speculation. Behind the formal tone was a deeper admission that even with the best tools and methods, there are moments when the universe refuses to yield full comprehension. 3I Atlas had become more than a curiosity. It was now a symbol of the threshold between knowledge and ignorance, an example of how scientific inquiry encounters the limits of perception itself. The object continued its silent drift through the outer dark, indifferent to the debates it left behind. What it represented, whether a natural relic or an artifact of something far older and stranger, would remain unanswered, perhaps indefinitely. For now, the mystery of 3I Atlas existed as a point of reference, a reminder that even the most precise science is ultimately an attempt to interpret a reality that remains far greater than the instruments designed to measure it. In the months that followed 3I Atlas's departure from the inner solar system, the noise of speculation began to settle into something quieter, more methodical. The world's observatories, once overwhelmed by the strangeness of its behavior, turned to analysis, a patient dissection of light curves, velocity, data, and compositional models. From the chaos of early theories emerged a set of explanations that, while imperfect, stood on the foundation of established physics. They did not claim to solve the mystery entirely, but to describe its edges with the precision that science demands. These became known as the mainstream hypotheses, frameworks built not to enchant, but to endure scrutiny. The first among them was called the frozen shard hypothesis. It proposed that 3I Atlas was the remnant of a failed planetary formation, a fragment ejected from the outskirts of a newborn system before it could coalesce into a full world. In this view, it was not alien in origin, but ancient, natural, and scarred by time. Its irregular rotation, odd light reflection, and low density could all be the legacy of violent ejection, cryogenic preservation, and cosmic erosion. Laboratory models of interstellar ice mixed with refractory material supported this possibility. A blend of frozen gases and rocky inclusions could explain its reflective signature, too bright for a typical asteroid, yet too dim for pure ice. Over millions of years, radiation would have hardened its surface into a glass-like shell, a frozen witness of unfinished creation. A related, but more specific model, outgassing in shadow, offered an explanation for the subtle trajectory shifts that had perplexed astronomers. If the object retains volatile ices buried beneath its crust, they might sublimate only when shielded from sunlight. Instead of venting visible jets like a comet, these hidden emissions could occur within cavities or along shaded fractures, producing invisible but measurable thrust. The European Southern Observatory tested this hypothesis through thermal modeling and found that under certain temperature gradients, low-level gas release could mimic non-gravitational acceleration. It would not require exotic mechanisms, only geometry, shadow, and time. Yet the theory carried limitations: no coma, no detectable trace of vapor, and no infrared emission were ever observed. The data remained ambiguous, a solution that fit the equations, but not the silence of the sky. Another explanation focused on solar radiation, pressure, the steady push of photons against the object's surface. This was not a new idea. When light strikes matter, it imparts momentum, a faint but measurable nudge. For large, low-density structures, this pressure can subtly alter their trajectory. NASA researchers modeled 3I Atlas as an ultra-thin body, perhaps a fractured shell or porous aggregate, and found that its motion could indeed be replicated if its mass-to-area ratio were extremely low. The implication was that 3I Atlas might be far less dense than expected, more like cosmic foam than rock. But if true, it would mean the object had survived interstellar travel despite its fragility, crossing light years of radiation and dust without disintegration. Such endurance seemed improbable, yet not impossible. Then came the spectral illusion hypothesis, a humbler but essential reminder of the limits of observation. The color variations and reflective anomalies recorded by multiple telescopes might not belong to the object at all. They could emerge from the instruments themselves. Subtle calibration drifts, atmospheric distortion, or data compression artifacts. When signals approach the faint edge of detectability, even minor noise can appear as physical change. To test this, independent teams reanalyzed the spectral data using the James Webb Space Telescope's calibration models. Some inconsistencies vanished, suggesting that at least part of the mystery was an illusion born from the interface between light and technology. Yet even with corrections applied, a residual discrepancy persisted, small, but enough to keep the enigma alive. The final major theory among the mainstream set sought to trace 3I Atlas's origin, the stellar drift model, by backtracking its incoming trajectory through galactic coordinates. Researchers attempted to locate a system that could have birthed it. Simulations pointed loosely toward regions near Lyra, Cygnus, or Vega, sectors dense with young stars and protoplanetary debris. These stellar nurseries are cosmic foundries, places where gravity molds raw dust into planets and moons. If 3I Atlas originated there, it may have been expelled billions of years ago during the chaotic early stages of formation. Its journey across interstellar space would then represent a timeline beyond human comprehension, a single shard wandering between suns, while civilizations rose and fell unseen. Each theory, though grounded in reason, carried its own contradictions. The frozen shard required endurance against cosmic radiation that no known composite could sustain. Outgassing demanded hidden volatiles that no sensors detected. Radiation pressure implied a structure so thin it bordered on the artificial. Spectral illusion blamed the tools, yet the tools had been checked and recalibrated. And stellar drift left too many paths, too many uncertainties lost to the vastness of time. Still, what united these models was not their accuracy but their humility. Each accepted that 3I Atlas might be extraordinary, yet still belong to nature's vocabulary. The object did not need to be alien to be astonishing. Every anomaly could, in principle, be the product of processes that have occurred countless times before, unseen and unrecorded. In that perspective, 3I Atlas became less an exception and more a revelation, a glimpse into how diverse and unpredictable the universe's creations can be. The importance of understanding such an object extended far beyond curiosity. Interstellar visitors like this one serve as archives of cosmic history, carrying chemical records from environments untouched by the sun's influence. Studying them could refine our models of planetary formation, migration, and destruction. They are messengers from systems long gone, carrying within their atoms the story of how worlds are born and how they end. Even if 3I Atlas proved to be nothing more than a fractured stone drifting through the dark, it would still represent something profound, a physical connection between our solar system and the rest of the galaxy. In the end, the mainstream theories did not close the case. They only mapped the perimeter of understanding. Beyond that boundary waited the more radical possibilities, ideas that challenged not just astrophysics, but the assumptions of reality itself. Those theories would come next, in whispers of speculation that dared to imagine what the data could not confirm, yet refused to deny even as the mainstream explanations gained academic traction. Subtle inconsistencies refused to fade. The data, examined from every possible angle, continued to whisper of irregularities that no single theory could encompass. The international collaboration between NASA, the European Southern Observatory, and the Japanese Subaru telescope pushed the limits of modeling, feeding every observation into supercomputers designed to simulate millions of potential evolutionary paths. None matched the object's recorded behavior precisely. The velocity decay curve remained slightly asymmetric, and the rotational light signature changed in ways that defied the uniformity expected from a purely natural body. For the scientists involved, this inconsistency was not a flaw in their calculations, but an invitation, a challenge to the very definitions that had long governed celestial mechanics. In the context of the frozen shard hypothesis, researchers at the Max Planck Institute for Astronomy revisited data from Oumuamua, comparing spectral fingerprints line by line. 3. Atlas shared similarities, but not enough to form a lineage. Its albedo ratios were higher, its surface temperature response flatter. If it was a remnant of planetary formation, it came from a system with chemical ratios unlike any known nearby stars. That hinted at an origin outside the galactic neighborhood, possibly from a region with different metallicity, farther toward the galactic arm. Such a possibility suggested it had traveled not just millions, but hundreds of millions of years to arrive here, crossing interstellar densities thin enough to make a single dust grain rare. Its survival over such distances continued to confound material science models, which predicted disintegration long before it could have reached the solar system. Meanwhile, teams analyzing the outgassing in shadow model began to consider less conventional sources of propulsion. Instead of volatiles like carbon dioxide or ammonia, they examined the possibility of sublimating exotic ices, nitrogen, carbon monoxide, or even trapped noble gases. These substances, though rare, could theoretically produce thrust without a visible coma under specific conditions. Simulations performed at the Jet Propulsion Laboratory showed that nitrogen ice, when covered by a hardened crust, could vaporize slowly and create measurable non-gravitational acceleration. It fit the data almost perfectly, until calculations revealed that the required nitrogen mass would be too large to remain stable over cosmic time. The theory was not dismissed, but it drifted toward uncertainty, another near solution that faded upon close inspection. The solar radiation pressure theory also evolved. As the James Webb Space Telescope collected refined infrared data, scientists began reevaluating its implications. If the object truly responded to photon pressure, its density would have to be lower than any naturally formed rock or ice. Some speculated it might be a porous aggregate, a cosmic dust sponge created by microcollisions in protoplanetary disks. Yet the data also suggested a degree of uniformity in reflectivity inconsistent with such fragile structures. Others pointed to molecular layering, proposing that 3I Atlas had developed an ultra-thin reflective crust after eons of exposure to interstellar radiation. This crust, composed of carbon-rich compounds, could explain its resilience, a natural armor forged by time itself. The theory fit elegantly within the framework of known physics, but lacked direct confirmation. It was a story told through probability, not proof. When the spectral illusion model was revisited, it became clear that while instrumentation accounted for part of the color variation, some residual features were intrinsic to the object. Near-ultraviolet spikes in its spectrum did not correspond to any known mineral signature. The readings suggested complex organic molecules, phollins perhaps, or carbon nitrides, materials that form under intense cosmic radiation. Their presence would not be extraordinary in isolation, but their distribution across the object's surface appeared too uniform. Some researchers proposed that cosmic rays had gradually polymerized its surface into a dark, glass-like coating. Others speculated that its uniformity could imply rotational resurfacing, a process where micro-collisions continually refresh the exterior. Both ideas remained plausible, yet neither resolved why the spectral response shifted subtly as it passed the solar limb. Finally, the stellar drift theory continued to haunt the discussion. Each attempt to trace the object's origin pointed toward a different region of the galaxy, depending on how gravitational perturbations were modeled. Some vectors led toward the Vega system, others toward the Hercules-Lyra boundary. The margin of error grew exponentially with each extrapolation backward in time. After 1,000,000 years of travel, even the smallest uncertainty in velocity produced deviations spanning light years. The truth of its birthplace might therefore be permanently lost, erased by the chaos of interstellar motion. For some, that realization was quietly devastating. For others, it added to the beauty of the discovery that something could wander across the galaxy unclaimed, untethered to any known world. Through all this, the scientific community reached a reluctant consensus. 3I Atlas was most likely natural, yet unlike anything previously recorded, it was a product of cosmic conditions not yet fully understood, a testament to the diversity of processes that shape matter in deep space. Its study expanded the boundaries of astrophysics, forcing models to grow more complex, more adaptive. Each observation became a reminder that nature's capacity for invention exceeded human expectation as the data accumulated and the models stabilized. One truth became apparent: the mainstream theories had mapped the visible terrain of understanding, but just beyond their reach, there lingered something that refused definition, a faint signature in the light curve, a curvature in its path, a silence between the readings. That silence was not noise. It was a question, waiting for a new kind of science to answer. Among the countless ideas born in the wake of 3I Atlas, some took root not in laboratories, but in the boundless spaces of imagination. When data defied explanation, the conversation expanded beyond equations and into the quiet territory between science and wonder. For centuries, astronomy had balanced on that threshold, between what could be measured and what could only be felt. The case of 3I Atlas reminded the scientific world that progress often begins in that uncertain middle ground. The first of these speculative notions, cautiously whispered in private discussions before finding their way into late-night conferences and online forums, was the artificial origin hypothesis. To some researchers, the uniform reflectivity, precise angular momentum, and subtle acceleration of 3I Atlas echoed the same questions once asked about Oumuamua. The idea was simple but provocative. Perhaps this was not a random fragment of nature, but a relic of intention, a shard of something engineered long ago and far away. Papers emerged proposing that the object's apparent non-gravitational motion could be the result of a thin, sail-like geometry. A few scientists at Harvard Center for Astrophysics revisited earlier work on light sails and their interactions with stellar radiation. They found that, theoretically, a wafer-thin object of the right composition could achieve a trajectory matching 3I Atlas's observed path. No evidence proved it, but neither could it be dismissed entirely. Those who favored natural explanations criticized the lack of material data, the absence of any detectable radio signature, the irregular light curves inconsistent with controlled orientation. But even within the skepticism, curiosity persisted. If 3I Atlas was artificial, it might not be a functioning device. but the remnant of one, a derelict probe, broken by time, a fragment of a structure once vast, now reduced to drifting debris. In that scenario, its silence was not defiance, it was decay. Another idea emerged, both stranger and rooted in advanced physics, the exotic matter core hypothesis. It arose from an anomaly in mass estimation. When researchers modeled its motion relative to solar radiation and gravitational pull, they found discrepancies suggesting a mass-to-size ratio beyond normal parameters. Some proposed that it contained a region of altered density, perhaps even a pocket of trapped dark matter. Though speculative, the concept found traction among physicists studying gravitational interactions on small scales. If dark matter could be briefly bound with an ordinary material, perhaps during an extreme astrophysical event, its presence could distort local gravitational behavior. This, in theory, might explain the minor irregularities in 3I Atlas's deceleration, without invoking artificial propulsion or errors in observation. Yet, without a sample or close encounter, the hypothesis remained little more than a mathematical echo, possible but unreachable. The notion of a relic of a lost civilization carried a different kind of gravity. It was less about physics and more about perspective. The idea that advanced life elsewhere might have risen, built, and vanished long before Earth's species learned to speak was not new. But 3I Atlas gave it form, an object without a home, scarred by ages, moving with a purpose that no longer existed. To those who entertained the idea, it symbolized the inevitable trajectory of intelligence, to create, to explore, to fade. If this object was indeed a fragment of a civilization's legacy, it had traveled across epochs, not as a messenger, but as a ghost. Its path through the solar system became a silent reminder that time erases even the greatest builders. No alien signal would follow, only reflection, both literal and philosophical. Others pushed the discussion beyond the tangible. A small group of theoretical physicists proposed that the 3I Atlas might not be a solid object at all, but a dimensional scar, a ripple left in space-time by an ancient astrophysical event. The idea, derived from models of gravitational wave interference, suggested that intense distortions could, under rare conditions, leave semi-stable geometric anomalies. If such an event had occurred millions of years ago, the scar could manifest as a coherent structure moving through the cosmos, bending light and matter in unusual ways. Its apparent reflectivity might be an illusion, light curving through a warped region, creating the semblance of a physical body where none truly existed. Though speculative to the extreme, this interpretation fascinated those who studied the boundary between relativity and quantum geometry. It implied that 3I Atlas might be not an intruder from another world, but a fragment of the universe's own memory, a ripple of creation still echoing across time. Perhaps the most abstract idea came not from astronomy but philosophy, the simulation glitch hypothesis. It appeared in essays and conferences where the language of science met the metaphors of digital theory. If the universe was a computational structure, a simulated reality operating under fundamental rules, then 3I Atlas might represent a rendering anomaly, a data fault in the cosmic code, a phenomenon that should not exist, yet does, precisely because the system that governs existence is not perfect. While such ideas stretched far beyond empirical science, their emergence reflected a deeper truth, that every generation of thinkers confronts mysteries that challenge not just their models, but their sense of reality itself. Through it all, one idea threaded these speculations together: the human need to dream beyond proof. Every theory, however outlandish, spoke to a shared instinct to reach toward meaning in the unknown. From Galileo's trembling sketches of moons to the vast simulations run on quantum computers, humanity's pursuit of understanding has always balanced on imagination's edge. Science advances not only through data, but through daring the willingness to imagine that reality may be stranger, deeper, and more connected than current knowledge allows. 3i Atlas, whether a relic of nature or the artifact of something far greater, became a mirror for that impulse. It asked no questions, but inspired countless ones. It offered no answers, yet deepened the desire to seek them. And in that way, it fulfilled the oldest function of discovery to remind a species, small against the scale of the cosmos, that mystery is not an obstacle to knowledge, but the very force that propels it forward. As data continued to accumulate, a quieter transformation began within the scientific community. The speculative theories that once hovered on the periphery started to attract rigorous attention, not because they were necessarily true, but because every conventional path had reached a dead end. The simplest explanations failed to align with the evidence, and 3i Atlas forced scientists to reconsider boundaries they had assumed were fixed. What had started as fringe discussion began evolving into structured inquiry, with interdisciplinary teams reanalyzing the available data from new angles. Astrophysicists began running models that incorporated non-standard physics. Some simulations used modified parameters for radiation pressure and particle cohesion, testing how thin, layered materials might behave in interstellar space. These models were inspired by known structures such as graphene or cosmic dust aggregates, but the goal was to see if a natural formation could produce similar reflective and rotational characteristics to what was observed in 3i Atlas. The results were inconclusive, but intriguing. Certain simulated materials demonstrated the ability to maintain stability under intense stress, while reflecting light in unusual polarization patterns. Though none could fully reproduce the observed motion, others turned to high-energy astrophysics. If 3i Atlas had passed near a neutron star or through a supernova remnant, its structure could have been altered by intense radiation or magnetic fields. Under such conditions, ordinary matter can undergo transformations not found anywhere within the solar system. Atomic lattice may rearrange, creating exotic crystalline phases capable of unusual optical properties. Researchers speculated that this might account for the variable reflectivity and nonlinear acceleration patterns, although such events would be exceedingly rare. Tracing its trajectory backward through space, scientists searched for any likely point of origin that matched these extreme environments. None yet fit with certainty, but several regions near the Cygnus arm remained candidates. Meanwhile, cosmologists began revisiting theoretical frameworks dealing with space-time curvature and non-local effects. If gravity could influence an object not only by mass but also by its prior interactions with curvature, what some referred to as gravitational memory, then perhaps 3i Atlas's path represented a residual effect of previous encounters. The mathematics was complex and untested, but it offered a way to explain the subtle deceleration without invoking propulsion or exotic materials. If confirmed, such an effect could provide insight into how objects preserve gravitational information over vast timescales, potentially opening new avenues in general relativity and cosmic topology. The speculative momentum also drew interest from engineers and materials scientists. Even if 3i Atlas was entirely natural, its endurance presented a valuable mystery. Understanding how an object could survive millennia of interstellar bombardment without disintegration could inform spacecraft design, shielding concepts, and artificial sails meant for deep space travel. The Breakthrough Starshot Initiative and similar programs quietly followed the findings, examining whether data from 3i Atlas could improve understanding of microscale structures interacting with radiation and plasma. The mystery, while unsolved, began generating practical benefits, a pattern often seen in scientific progress. In philosophical circles, the discussion took on a more measured tone. Theories once dismissed as speculation were reconsidered as exercises in perspective rather than literal truth. The notion that 3i Atlas might be a relic, a dimensional artifact, or even a symptom of flaws in human perception underscored how observation itself defines understanding. When instruments reach their limits, the boundary between data and interpretation becomes uncertain. It was no longer about confirming or denying exotic hypotheses, but about acknowledging how each attempt to explain the unknown reveals the current limits of comprehension. Across institutions, researchers began to coordinate more transparently. International working groups compiled all known data, including archived photometric and spectroscopic records from telescopes not initially focused on the object. Subtle discrepancies between datasets were identified, but rather than resolving the puzzle, they deepened it. Polarization readings remained inconsistent yet statistically valid, meaning the unusual reflective properties could not be dismissed as mere artifacts. By the time the object left measurable range, consensus had not been achieved. Yet, in that lack of closure, a new form of progress emerged. The first atlas had expanded the boundaries of inquiry beyond its physical existence. It had pushed scientists to confront uncertainty as an integral part of discovery, not a failure of it. Each speculative idea, however unconventional, had acted as a stress test on human logic, exposing how much of science depends on the courage to question even foundational assumptions. In the end, no single theory could define what 3i Atlas truly was. Whether shard, remnant, artifact, or anomaly, its greatest contribution lay not in what it revealed, but in what it demanded. To understand something that resists explanation is to move closer to the frontier of knowledge itself, where established truths give way to possibility, and the search for meaning continues, quietly, through the dark, even as 3i Atlas fades beyond the range of human observation. Its trace continues to ripple through the corridors of science. Around the world, the pursuit of its secrets has not ended. Instead, it has evolved, becoming quieter, more methodical, and infinitely more determined. What was once a fleeting glimmer against the backdrop of the sun has transformed into a shared mission, to reconstruct a story from particles of data, to hold on to the final echoes of a visitor now lost to interstellar night. From observatories in Chile to deep space monitoring stations across Europe and Asia, a silent network continues to follow what remains of 3i Atlas's signal. Its light is gone, yet its path persists, a faint coordinate in the collective map of the cosmos. These facilities, linked through the International Astronomical Union and supported by independent networks of researchers and amateur astronomers alike, maintain the faint thread of tracking data that still defines the object's journey. Each fragment of telemetry is logged, recalibrated, and shared across digital repositories that store not just observations, but the fading heartbeat of a mystery that refuses to vanish. The James Webb Space Telescope, with its unparalleled infrared sensitivity, became a crucial part of this pursuit. Although 3i Atlas has long since slipped beyond Webb's direct line of sight, archived infrared data from its earlier approach is being revisited with new calibration models. Even the subtlest fluctuations in its thermal emission could hold information about composition, how metals, silicates or volatile compounds reflected and absorbed sunlight across the electromagnetic spectrum. Scientists reanalyze these frames pixel by pixel, searching for spectral fingerprints buried in noise. Some hope to detect molecular signatures, perhaps frozen, carbon compounds, or exotic silicate arrangements that might reveal how the object formed. The upcoming Vera-C-Rubin Observatory, expected to revolutionize transient sky observation, represents the next frontier. Its wide-field survey will scan the entire visible sky every few nights, offering an unprecedented chance to detect new interstellar visitors before they vanish. If 3I Atlas was one of many, Rubin may soon reveal the pattern, a hidden current of wandering interstellar debris crossing the solar system each decade. Detecting these objects early could allow for rapid response missions, designed to observe or even intercept them before they recede into the dark again. Parallel to these observational efforts, another discipline quietly advances: data reconstruction. Artificial intelligence and machine learning systems now reprocess all recorded imagery of 3I Atlas using algorithms trained to detect faint signatures once lost to instrumental limitations. This approach has already led to minor breakthroughs, subtle corrections in its photometric curve, adjustments in the estimate of its albedo and rotational period. Some models even suggest that what once appeared as erratic brightness variations may have followed a predictable modulation pattern, hinting at layered surface structures or complex rotation. These insights, small as they are, demonstrate how digital intelligence can extend the reach of human perception, a form of seeing beyond time itself, beyond observation. Imagination has begun to merge with engineering. Space agencies and private research groups have quietly drafted theoretical mission concepts, spacecraft capable of reaching future interstellar objects with unprecedented speed, designs for laser-propelled sails, autonomous microprobes, and plasma-assisted propulsion engines have all entered simulation. The concept is simple but revolutionary: to chase the next interstellar visitor before it escapes. In workshops at NASA's Innovative Advanced Concepts program and among independent engineers, 3I Atlas is frequently referenced as the test case that got away. It stands as both warning and motivation, a reminder that discovery means little if not followed by readiness. The field of interstellar object science, once non-existent, is now rapidly growing. Almamua in 2017, Borisov in 2019, and 3I Atlas in 2020 mark only the beginning. Statistical models predict that the solar system may encounter such travelers every few years, though most pass unnoticed. New detection systems, both ground-based and orbital, are now tuned to identify the telltale signatures: unusual velocity, non-bound trajectories, and irregular light curves. Each future discovery will expand humanity's understanding of the galactic environment, the debris of distant star systems, the relics of ancient collisions, perhaps even the remnants of worlds long gone. Yet within all this technological progress, there remains a quiet acknowledgement that the vast majority of interstellar visitors will never be seen. They will drift silently through the inner system, invisible against the glare of the sun, carrying with them the untold histories of alien skies. The universe, as some astronomers quietly say, is likely teeming with such wanderers, frozen archives of forgotten systems, endlessly crossing the interstellar gulf. 3I Atlas was simply one that chose to reveal itself, briefly, before continuing its solitary voyage. In the laboratories and control rooms, where its data still flickers across monitors, the atmosphere is no longer one of urgency, but of reflection. The pursuit has evolved from chasing an object to contemplating its meaning. Humanity has begun to see interstellar visitors not as anomalies, but as emissaries, messengers from a galaxy-wide continuum of birth, decay, and motion. Each one challenges assumptions about what belongs to our solar system and reminds us how porous the boundaries of cosmic ownership truly are. Somewhere, beyond the Heliopore's 3i, Atlas continues its journey. Its trajectory bends gently toward the outer constellations, perhaps into the void near Lyra, perhaps beyond the reach of any future instrument. Its light is gone, but its effect endures. In observatories, in equations, in silent debates late into the night, its presence remains a question that continues to orbit the human mind. And through that question, the species that once watched from a single pale planet keeps learning to look a little further, to listen a little deeper, and to wonder without end. The pursuit of 3i Atlas did not end when its light faded beyond the limits of telescopic detection. Instead, it transformed into a new phase of inquiry, one that exists not in the sky, but within the data itself. Every recorded photon, every marginal reading from observatories across the world, is now part of an ongoing digital excavation. Scientists no longer look at the object directly. They look through the numbers, through the uncertainty, reconstructing its nature from patterns that sit just above the threshold of noise. At NASA's Goddard Space Flight Center, archived data, streams from 2024, are being reprocessed with new computational models, capable of simulating interstellar illumination under variable solar radiation conditions. These simulations attempt to account for how the object's surface might have responded to uneven solar heating during its perihelion, a factor that could explain the non-gravitational acceleration once observed. In other labs, deep models are trained to differentiate genuine material reflections from optical interference, narrowing the gap between instrument error and real anomaly. The goal is no longer to prove what 3i Atlas was, but to eliminate what it could not have been. Meanwhile, a growing coalition of observatories continues to refine techniques for detecting similar interstellar visitors. The European Southern Observatory has begun integrating adaptive optics with real-time motion prediction algorithms, allowing their telescopes to lock onto faint, fast-moving objects without manual correction. This system, once perfected, could capture sharper, more continuous data streams than were ever possible during the brief passage of 3i Atlas. Each technological refinement is driven by a quiet acknowledgement that the next interstellar object could appear at any time, and humanity cannot afford to watch another one slip away. In academic circles, the legacy of 3i Atlas has shifted from direct observation to theoretical interpretation. Research papers now discuss it as a boundary case, a phenomenon that resists classification under existing astrophysical categories. Its anomalous reflectivity and irregular acceleration remain points of contention, sparking debates about whether known mechanisms like outgassing or radiation pressure are sufficient to explain its movement. Some scientists suggest that 3i Atlas may represent a transitional type, an object forged in an environment unlike anything in the local stellar neighborhood, possibly from a system whose chemistry never resembled our own. Theories extend into chemical models that simulate exotic combinations of metals and carbon structures, potentially hardened by cosmic radiation over millions of years of interstellar drift. As observation gives way to simulation, 3i Atlas has become a case study in the evolution of scientific methodology. It demonstrates how data, integrity, cross-disciplinary collaboration, and computational innovation now define the future of astronomy. The object's mystery has outlived its visibility, and in doing so has forced a subtle shift in the culture of research itself. The emphasis is no longer on what the eye can see, but on what the machine can infer. Modern astronomy, as many now argue, is entering a phase where discovery will increasingly emerge from reinterpretation rather than direct detection. In parallel, a new generation of mission designers continues to refine plans for intercept probes. Concepts like NASA's Comet, Interceptor, and ESA's Foresight have become prototypes for more advanced systems. Small, autonomous craft capable of launching on standby and redirecting within hours toward an unbound interstellar trajectory. These spacecraft would not merely observe, but sample, collecting dust grains, imaging structure in detail, and returning direct chemical analysis. The challenge lies not in the technology alone, but in readiness. Interstellar visitors do not announce their arrival. They must be caught in the act of passing. The hope of such missions rests on improved early warning systems. Optical and infrared survey arrays, assisted by artificial intelligence, now continuously monitor vast swaths of sky for fast, non-repeating motion. Algorithms trained on previous detections, Oumuamua, Borisov, and 3I Atlas, can identify potential interstellar candidates within hours of discovery. The moment one appears, protocols are ready to mobilize telescopes, satellites, and deep space assets simultaneously. Humanity is, for the first time, preparing not just to watch the next visitor, but to meet it. And yet, even amid technological progress, there remains a quiet humility among researchers. They know that for every detected traveler, countless others drift unseen through the solar system, fragments of distant histories, bearing no light strong enough to betray their presence. The cosmos does not reveal its wonders all at once. It offers them sparingly, in glimpses and echoes. 3I Atlas may have been one such offering, a single, fleeting signal reminding the species that its understanding of reality is still narrow, still provisional. In that sense, the object's disappearance was not an end, but an invitation. It drew attention to the limitations of human perception and technology, and to the boundless expanse that lies just beyond them. The pursuit continues, not out of obsession, but out of necessity. For every mystery, like 3I Atlas, science expands the edge of what can be known. And somewhere in that expansion, between data and imagination, between light and distance, the next revelation waits, another object, another signal, another reminder that the story of the universe is still being written, piece by piece, visitor by visitor, light by fading light. In the quiet aftermath of discovery, when data fades and telescopes turn toward new horizons, what remains is not the object itself, but the echo of its passing. 3I Atlas is no longer a bright point of study on digital screens or a stream of numbers, flowing through observatory servers. It has become something else, a question, suspended in the collective mind of a species still trying to understand what it means to observe, to interpret, to know. Every interstellar visitor forces humanity to confront the boundaries of its own comprehension, to look not only outward into the vast cold expanse, but inward toward the fragile machinery of its own curiosity. For centuries, the pursuit of knowledge has been both a triumph and a burden. Each new discovery, whether a planet, a particle, or a ghostly interstellar shard, reminds the observers that the universe is far less about answers than it is about perspective. 3I Atlas, with all its unresolved anomalies, carries this truth like a silent teacher. It arrived uninvited, defied expectations, and left without explanation, a perfect embodiment of cosmic indifference. Yet, in that indifference, humanity found reflection that the universe owes no clarity, and meaning is something the observer brings, not something the cosmos provides. Scientists still debate what 3I Atlas was, a fragment of a distant world, an eroded interstellar comet, or something beyond the scope of familiar classification. But beyond the data, it has become symbolic of something larger. Its fleeting presence has reshaped how researchers think about the limits of detection, the architecture of matter, and the fragility of cosmic understanding. It reminds them that observation is not merely an act of seeing, It is an act of interpretation, bounded by the tools, biases, and imagination of those who wield them. In philosophical terms, 3. Atlas occupies the same space as all great unknowns.